So in this part, I will talk about what does the quantum dot solar cells bring to the table with respect to the conventional solar cells. This slide here represents the outline, and I will start explaining the Shockley-Queensey limit. So this figure here represents the solar spectrum with respect to the wavelength. So if the photon has a wavelength which is higher than 1000 nanometer, the silicon material will be transparent and the energy loss is estimated to be 20%. If the photon energy is smaller than 1000 nanometer, the silicon material will absorb this photon more or less depending on its quality. In the same time, if we have a photon that has a wavelength smaller than 1000 nanometer, but it has a very high intensity, this photon will not be used and we will have a thermalization loss, and it's estimated to be 35%. So if we try to work on the thermalization area, the conversion efficiency can be increased up to 66%. So if we have a very high intensity photon which creates an electron hole pair, the electron will be in a very high energy state in the conduction band. This electron will have a temperature which is about 3000 Kelvin. This is why it's called hot electron. This hot electron will try to have the same temperature as the lattice, so which is about 300 Kelvin. So it will start thermalizing by emitting phonons. This phonon emission is the responsible of the 35% loss. There are several solutions in order to overcome the thermalization process. The first one is to use a stack of p-n junction, and the second one is to utilize the hot electrons. So we can use the stack of multiple p-n junctions with band gaps matching the solar spectrum. So the small band gap for the small energy and the higher band gap for the higher energy. However, one must take into account the compatibility of the stacks. With that being said, the atomic radius and the bonding between the junction. However, I will not go further into this because it's not the presentation topic. Today's presentation topic is more about the utilization of the hot electrons. So we can either collect them directly before they thermalize, or we can use them to produce other electron hole pairs through impact ionization. These two here are achievable via the quantization effect of the semiconductor. For example, quantum dots, quantum wires, and quantum wells. And here I will talk only about the quantum dots. So this here represents the quantum dot solar cell. So we have indium phosphide quantum dots with about 40 angstrom size, and here is the band gap. These indium phosphide quantum dots are chemisorbed on 300 angstrom TiO2, and here is its band gap. So when a high intensity photon creates an electron hole pair, this hot electron will not thermalize in this configuration. Instead, it will transfer directly to the TiO2 conduction band, and then it will be collected via the electrodes. Successful quantum dots have been done with indium phosphide, cadmium, selenium, cadmium sulfur, and lead sulfur. What's good about the quantum dot here is that we can change this band gap just by changing its size. The second solution is to use the impact ionization process. So impact ionization is the process of having a hot electron transferring directly to the edge of the conduction band. I repeat, it transfers directly. It will not go into the energy states one by one. It will transfer directly to the edge of the conduction band, releasing an energy. This energy in excess will be responsible for creating another electron hole pair. So with only one photon, we have created two electrons. So the quantum yield here is 200%. So you might say, hey, the hot electron should thermalize. We should have phonons. Yes, you are right. So for example, if we see in the bulk here, since the energy separation between the states in the conduction band is smaller than the phonon energy, the hot electrons will thermalize and they will emit phonons. However, with the quantum dots, these energy separations are tunable. We can change them just by changing the size. So if we can make the energy separation higher than the phonon energy, we will favor the impact ionization process instead of the thermalization process. And sometimes when the hot electron transfers to the edge of the conduction band, its energy is enough to make 3 or 4 electron hole pairs. So the quantum yield can be achieved up to 300 or 400%. So to conclude, the quantum dot solar cells are useful in order to extract the hot electron directly before they thermalize, only with this configuration. Or we can use them in order to favor the impact ionization process by creating other electrons. However, we cannot use the two. I mean, this one and this one. We can use either this one or the previous one. And that's it. Thank you.